All right, today we're going to talk about the basics of what a limit is. We're not going to use the delta epsilon definition. We're just going to use what our intuitive understanding is for a limit in mathematics. Okay, so initially we're going to discuss what is a limit. Well, a limit is nothing more than a y value that you expect to approach when x gets really close to a number on your function. So, for example, I've drawn a picture of a function I call f of x here, and it's got a removable discontinuity at x equals 4. All right, and so let's say I want to find the limit as x approaches 2. And this is the notation that you would use. The limit, LIM, is short for limit, and x approaches 2 has to directly be beneath the LIM, and then f of x is in line with the LIM here, okay? So what this means is, when we say it, the limit of f of x as x approaches 2, all right? So what is the limit of f of x as x approaches 2? Well, as x gets closer and closer to 2, if you are on your function, your y value or your f of x value gets closer and closer to 1. All right, so that's what it is. It's a singular value for y that your function approaches as x gets closer to a number. Okay, all right. So let's try the limit as x approaches 4. So my limit of f of x as x approaches 4. Well, as x gets closer and closer to 4, my y value gets closer and closer to, well, there is no y value here. The function doesn't exist here, but the limit does, because the limit is the y value that I expect to approach or expect to reach as x gets closer and closer to 4. So as x gets closer and closer to 4, I would expect the y value or the function value to get closer and closer to, in this case, 2. So you can have a limit that is not equal to the function value, which can be a little tricky, but it's not impossible. And then we can have limits we call end behavior limits, the limit of f of x as x approaches infinity. Well, that means as x goes to infinity, which is all the way down here and beyond, what is the y approaching? Well, in this case, the y appears to be going on towards infinity, so this would be infinity. And let's do the other end behavior limit. The limit as of f of x as x goes to negative infinity. All right, so we go this direction in the x direction, and the y is going to go also to positive infinity. And we call these end behavior limits because those are the behaviors of x as it gets to the end of the graphs. Now, these we call, that we did up here, two-sided limits because I have a limit from the left and a limit from the right. I can call them one-sided limits. All right, and how would I write that out? Let's say I wanted the limit as x approaches 2 from, I can designate it with a superscript with a negative sign or a minus sign. So this, you read this, limit of f of x as x approaches 2 from the left side. Okay, so let's look at our graph. So as x gets closer and closer to 2 from the left side, my y that I expect to approach, or the limit of my function, is going to approach 1. We call this a one-sided limit because we're coming at the x from one side and thus the y from one side. Well, in this case, I have two sides. So I can say the limit as x approaches 2. We can also come at it from, we use a positive to designate the right side. So the limit of f of x as x approaches 2 from the positive side. So let's go from the positive side. As x gets closer and closer to 2 from the positive side, my function gets closer and closer to 1 from the positive side. Now in this case, those limits are equal. So therefore, the limit as x approaches 2 from both sides, which is what this implies, exists because we're approaching a singular y value. Okay, so this generates perhaps us having a discussion on when a limit doesn't exist. So let's do that really quickly. So when does a limit not exist? Okay, when does a limit not exist? Well, I think I've summarized it in my own mind as to 4 reasons. Okay, so let's start, and let's say this is reason number 1 here. Trying to get it lined up here. So reason number 1. So a limit doesn't exist when the one-sided limits as x approaches a, and a is some number that you're approaching, are not equal. All right, so let's do a graphic representation of a situation where that might occur. Now I'm just graphing a random graph here. I've got a line with an open point here and a solid point here, and we'll just make a parabola that opens down just to be a little bit different. Okay, so this is x and this is y, and we're going to call this, in this case, we'll say a is 1, okay, because this is approach just any number, but we're going to say a is 1 here. Okay, and this is 1 and this is 2. The one-sided limits here, the limit as x approaches 1 from the left of our f of x here, the limit as x gets closer and closer to 1 from the left side, the y, or the f of x, is approaching 1. All right, the limit as x approaches 1 from the positive side, or the right side, as x gets closer and closer to 1 from the positive side, or the right side, the y is approaching, or the f of x is approaching 2. Okay, but however, if I said the limit as x approaches 1, and I don't designate a left or a right, or use a plus or a minus here, implies that I am considering it from both sides. Well, here, the limits from the left and the right are not equal, so this we would designate as does not exist. Okay, because we're not approaching the same numerical value. Now, and in calculus, and in pre-calc, when you are designating a limit that doesn't exist, you should explain mathematically why, and we're going to use the since notation. How do we know it doesn't exist? Well, we know because the limit as x approaches 1 from the left side is not equal to the limit as x approaches 1 from the right side. Okay, and I would want you to tell me what those limits are. 1 is definitely not equal to 2. Okay? Now, there's another time when the limits are not equal, and that's if you have a vertical asymptote. So let's draw that really quickly. And I'm going to be boring and do it at 1 again. And do a rational function here where we have, function that looks very rational in nature. And math is rational. We like that, don't we? All right. So in this case, the limit as x approaches 1 from the left, well, as x approaches 1 from the left side, or the negative side, where my y value is approaching infinity. The limit as x approaches 1 from the right side, in this case, as x gets closer and closer to 1 from the positive side or the right side, that's negative infinity. All right, now, those are different values of infinity. So when I would say the limit as x approaches 1 from the implied both sides, I would say does not exist here. And I would say for the same reason, is that the limit as x approaches 1 from the left of f of x is not equal to the limit as x approaches 1 from the right. And we would say that infinity is definitely not equal to negative infinity. All right, so those one-sided limits are not equal. Okay, so that's the first case. The second case, when limits don't exist, would be that a function doesn't approach a finite value. Now, finite is different than infinite, right? Now, you might say, well, but Mrs. Muller, we just did one that had a limit that didn't approach a finite value. All right, and I should say here as x approaches a. All right, so let's draw a picture of one. So I'm going to draw, whoops, helps if I stay on the lines, right? That's why I have a piece of paper with lines, so I can stay on the lines. Okay, so let's draw, let's try 2 this time. Let's do a vertical asymptote at 2. So this is 2. And I'm going to draw my vertical asymptote here, and I'm going to approach it this way. All right, and this is my f of x. The limit as x approaches 2 from the left side here is infinity, isn't it? But is this a finite value? The answer is no, it's not a finite value. But we don't say it doesn't exist here, okay? Because it's convention to write it as infinity, which is the direction that it's going. Okay, so when you write infinity, you're writing it doesn't exist in your mind, but you wouldn't say D and E here, you would write infinity, okay? Another case would be, let's do another case here so I can stay on the same page. Let's just use our, classic x squared. And right, we would say the limit then, as x approaches infinity now, of x squared equals, well, what happens as x approaches infinity? Well, x squared is rocketing off to infinity here, which does not exist, but this is not a finite number, so technically the limit doesn't exist, but we are, by convention, writing infinity here because that's where our function is headed. Okay? Now, let's say we have one last situation in this category. Let's say I have a rational function that has a bounce. And what do I mean by that? That means I have a multiplicity of 2 in the denominator. And I'm going to say that my function looks like this, roughly. And I'm going to say f of x here is equal to 1 over x minus 2 quantity squared. Okay, so I have a bounce in the denominator, so it bounces at infinity up here. Now, the left-handed limit here, the limit as x approaches 2 from the left is equal to infinity. The limit as x approaches 2 from the right of here is also infinity. And the limit as x approaches 2 from both directions. Now, these are not finite answers, but we're designating the direction. And because they're headed to the same infinity here, we would say that the limit as x approaches 2 is going to infinity because they are the same direction. Unlike the situation we had up here on this rational function where the infinities were different. Okay, so this one also does not exist, but it's headed to the same infinity. And by convention, we would write infinity here as opposed to does not exist. All right. Here's another case. I'm going to have, I think, 3 bullet points here. All right, so number 3, for a reason for a number, one to not exist. All right. A function does not approach a single finite number for example. Now, the example I'm going to use is f of x is equal to the sine of 1 over x minus a. Now, in this case, and I'm going to do a Desmos graph here, and we're going to say y equals sine of 1 divided by, let's do x minus 2, okay? Now, when you look at this graph on Desmos, I want you to notice that as we get closer and closer to 2, boy, this graph is bouncing all over the place. It's bouncing between two distinct numbers, isn't it? It's bouncing between 1 and -1. And so in that case, the limit as x gets closer and closer to 2, and I mean, we could sit there and try to get closer and closer to 2, but we're going to see that we have what we call infinite oscillations there at x equals 2. Okay, so in this case, the limit doesn't exist because we are bouncing between two different numbers, and which do you choose? Well, you can't choose one because we're bouncing between two different values. So in that case, the limit will also not exist. So that means that the limit as x approaches a of sine of 1 over x minus a does not exist because there are, you would say, since infinitely many oscillations, and we're going between -1 and 1 here, many as x approaches 2, right? So you can't choose a number because you're bouncing back and forth. So that's a limit that also doesn't exist, but it doesn't exist for the reason, the limit from the left doesn't equal the limit from the right. All right, so number 4, last one. All right, a function does not exist as x approaches infinity or as x approaches -infinity. Now, what do I mean by that? Let's consider f of x equals the natural log of x, okay? That's one of our toolkit functions from not too long ago. If I were to graph this is 1, and the natural log function looks like this, and it's approaching as x gets closer and closer to 0. It's got a vertical asymptote here at 0. Now, the log function doesn't have any domain to the left of 0. Okay, so in this case, we would say that the limit as x approaches 0 of the natural log function is equal to infinity. But what about the limit as x approaches -infinity of the natural log function? Well, goodness gracious, is the natural log function even over here at all when x approaches -infinity? And you can say dne here. And you don't have to justify this one because there just is no domain over here. The function has only domain starting at 0 and going forward, okay? There's another limit here that doesn't exist, and we can say that the limit as x approaches 0 from the positive side of our natural log function, well, that we know as x gets closer and closer, this is 1, so as x gets closer and closer to 0, the y value is approaching -infinity here, okay? But what about the limit as x approaches 0 from the left side? Well, does the function exist at all on this side? There's no function to be getting there is no x to be getting closer to, right? Because for these values of x over here, we don't have any function to be getting closer. So this one does not exist. And you don't have to justify that one either because there is no function over here. Now, I don't want to get that confused with the fact that when you have a removable discontinuity, there is no function here, because that's different. This is a break in the domain versus this one here, the domain hasn't even started yet. Okay, so that's how it's subtly different. All right, so I wanted to make sure that we understood the difference there. Okay, so those are kind of, in a nutshell, the 4 reasons why a limit might not exist. Okay, all right, so let's get to the guided notes that I gave you. And the left-hand limit, we said, is the limit of f of x as x approaches c from the left side. This would be the limit of f of x as x approaches c from the positive or the right side. And the general limit is from both sides. This is the limit of f of x as x approaches c. Okay, so now you might not be able to see this picture very well, but this is an asymptote here. This is indeed a function. It passes the vertical line test. So please note that this is not part of the graph. It's just I'm trying to show you or indicate that that's an asymptote that this function is approaching. Okay, and we're going to define this function as f of x, which I don't have designated on here, but we really should. All right, so let's fill out some limits looking at our graph. Okay, so the limit here of f of x as x goes to negative infinity. All right, well, so what happens is x is going to negative infinity. My y value that I expect to approach is 3. All right, next one we're going to do is x approaches, limit of f of x as x approaches negative 5 from the negative side or the left side. So I'm going to have x approach negative 5. The function is approaching from the left side 1. From the right side, so this says the limit of f of x as x approaches negative 5 from the plus side. Well, if I get closer and closer to negative 5 from the positive or the right side, the y value we are approaching is negative 2. All right. Well, we're making a mental note, right, that this is a jump discontinuity, to refresh our memory. Jump discontinuity, and the limit as x approaches negative 5 as our general limit, or from both sides, does not exist because, and we're going to say since, we're going to use our mathematical communications here, saying since the limit as x approaches negative 5 from the left side is not equal to the limit as x approaches negative 5 from the right side. And we can say that 1 is not equal to negative 2. So that's why that limit doesn't exist. All right, let's move forward. Next one. The limit of f of x as x approaches 0 from the left side. As we approach 0 from the left side, our function is approaching 4. The limit as of f of x as x approaches 0 from the positive side, as I get closer and closer to 0 in the x direction, the y is getting closer and closer to 4. The general limit, or the limit from both sides, is the limit of f of x as x approaches 0 from both sides is 4. Now, I don't have to justify it, but this one exists because the limit from the left is equal to the limit from the right. Next one. This one's a little bit tricky, but you guys can handle it. The limit of f of x as x approaches 2 from the left side. So as I get closer and closer to 2 from the x direction, the y is getting closer and closer to, what is the y that I expect to reach when I get to 2 in the x direction? Well, I expect to hit 0. But wait, my function value is up here and it says it's 5. If I am driving a shiny yellow Transformer Camaro on this function, and I get to this spot. What y value do I expect to hit, even though I might not hit it? Well, I expect to hit 0. So that's why that is 0. So the limit can be different than the function value. From the right side, same thing. As I get closer and closer to 0 in the x direction, the y is getting closer and closer to 0. And then the limit from both directions are both 0. So the limit does exist, and it's 0. All right, next one. The limit of f of x as x approaches 5 from the left side here. That means as I get closer and closer to 5 on the left side, my function is getting closer and closer to positive infinity. From the right side, as I get closer and closer to 5 from the right side, my function is getting closer and closer to, and my arrow should be here, not on the line, negative infinity. Well, what happens with the general limit now? Well, these are different. So we would say that this does not exist. And we have to say since, using our math language, the limit as x approaches 5 from the left of f of x is not equal to the limit as x approaches 5 from the right. All right. And then the last limit is as x goes to infinity. So what happens as x goes to infinity here? Well, the y value I expect to reach is negative infinity. All right, so that's just a basic, function that has a jump discontinuity. I say basic, right, because it's got all these discontinuities, so it's a little fancier than basic. But jump discontinuity, a removable discontinuity, and an infinite discontinuity all in one. All right, so let's look at a little bit more challenging problem here. And that one is if I give you some information, can you draw me a function given the limit descriptions? Now this one uses more abstract thought, but it's a really good exercise in in whether we understand limits and all the math language that's going on here. So I'll show you how I approach these kind of problems. So the first one says, or the instructions say, graph a sketch of a function. Now a function means it has to pass the vertical line test that has the following characteristics. And it gives me a bunch of limits, and it gives me some notation like this: f of 0 equals 3. Well, what does that mean? Well, this is a fancy way of saying the point 0, 3 is on my graph. And this one here also is a fancy way of saying the point 3, 4 is on my graph. So what I like to do is put my points that I'm given on the graph first, because those are the easiest things to do. Okay, so 0, 3 is on my graph, and 3, 4. So I'm going to put a 1, 2, 3 here. 3, 4 is on the graph. Okay, and they're solid because they are defined. All right, the next thing I do is I look at the infinities. That means as x goes to infinity or negative infinity. And the first one I reach is x approaches infinity. So the limit of f of x as x approaches infinity is negative 2. Well, what does that imply? As x gets closer to infinity, my function's approaching negative 2, which means I have a horizontal asymptote at negative 2. Now I have to approach negative 2 at the end over here. Now I don't know if I'm going to approach it from this side or this side, so I'm just going to leave this here as a reminder that that's what I have to approach. Okay. Now the limit as x approaches of f of x as x approaches negative infinity is infinity. So as I go this direction, I have to end up headed this way. So I'm going to just draw an arrow here because I know I have to end up that direction. And then I go from left to right, as my limits will dictate. So I notice that I have a limit as x approaches 0, 3, negative 2. So which one's the furthest left? Well, that's negative 2. Okay, so this says the limit of f of x as x approaches negative 2 from the left side is negative infinity, and from the right side it's positive infinity. So what does that imply? I heard it. That's right. It implies that we have a vertical asymptote at x equals -2. And on the left side, I'm heading to negative infinity. And on the right side, I'm headed to positive infinity. So I'm just going to put those there so I have an idea of the direction I'm headed. And then do I have anything in between negative infinity and -2? Well, it doesn't look like I do. And so I can just draw my graph on this side. Now, in class today, we drew something that looked like this. Okay. Now, you could have drawn anything that was a function as long as it approached this asymptote on the left side. Okay. Now, as I move from -2 to 0, I have some things to consider here. The limit as x approaches, the limit of f of x as x approaches 0 from the left side is 5. But wait, it says my function value at 0 is 3, but I have to approach 5 from the left side, which means for this to be a function, I have to have an open dot here at 5. And I have nothing else going in between, so I think I can just draw, me approaching 5 from the left side there. And then from the right side, my function has to approach 3. Well, I'm already at 3. So I think I'm coming out of here somewhere. I don't know where I'm going yet, but okay. Now let's see what's going on at 3. The limit as x approach, or of f of x, excuse me one more time. The limit of f of x as x approaches 3 is 2. Well, okay, but at f of 3, my function value is 4. But I'm approaching 2, which implies that I have an open dot here at 2. So I'm just going to draw a function here that approaches 2. Now this 3 doesn't distinguish, this limit doesn't distinguish a left and a right. So that means from both sides, it's 2. And then I have to approach this asymptote. So we can do a lot of different things as long as we're still a function, because it didn't tell us what we couldn't do. So I'm just going to do this and be wild and approach it from underneath. Could we have just drawn it and approached it from the top? Sure. But I was just being a little bit different. Now, what I do is I go through when I am done to check to see if I'm right by rereading all the stuff on the top and see if it matches. So the limit of f of x as x approaches 0 from the left side has to be 5. Well, as x approaches 0 from the left side, my function has to be approaching 5. That works. So I can say check. The limit of f of x as x approaches 0 from the plus side, as x gets closer and closer to 0 from the plus side, has to equal 3. Check. The limit as x approaches 0 does not exist. Well, these are different numbers, and certainly my graph has a jump going on here, so that is a check. I agree it does not exist. Now, I don't have to justify it here because I'm giving you that information. Okay, f of 0 is 3. F of 0 is 3. It certainly is. And then the limit as x approaches 3 is 2. So as x goes closer and closer to 3, my y gets closer and closer to 2. Yep. Then f of 3 is equal to 4. Yep. I should check this one. The limit as x approaches -2 from the left side is negative infinity. I can check that off. From the right side, it's positive infinity. And since they are approaching different infinities, the limit doesn't exist. And the limit as x approaches infinity is -2. I agree. And the limit as x approaches negative infinity is infinity. I agree. And so therefore, we have a picture that has all of those characteristics. Now, when you draw it, you might draw a different one, and that's okay. All right, so that's just a basic starter of limits graphically, and a little bit about when limits exist and when they don't, and that the fact that you can have a left hand and a right hand limit, and you can have a limit from both sides. All right, so you guys have a blessed day. Thanks.